Hello, today I'm going to show you how to scan an old surfboard and how to import the scan into Shape3d. So I'm using a hand laser scanner called Shape3d. This is a peel to model, but all I'm going to do can be done with the cheapest one, which is peel 1. So this is pretty plug and play. You just plug the laser on your computer and open the Shape3d software, and then you need to prepare the board a little bit. You don't need to remove the wax, but you need to mask the black logos. The best is to use white powder in spray, but if you don't have any, you can also use clear tape like this. And you can also mask the plugs, but it's actually not mandatory. The other thing you need to do is place targets given by Shape3d, like about every 20 centimeters. So this is needed to scan flat surfaces like the deck and the bottom. Once your board is ready, you just have to press start. And then you can scan the deck like this. So it can be done pretty quickly. Like you can do the whole deck with the targets very fast. If you go too fast, sometimes it can lose track of where you are, but then you can start over from a place you already scanned and keep scanning like this. And then you need to do the rails more carefully. For that, you need to go a little bit slower. The rails don't have targets, so sometimes it can lose track of where you are. So then you start over from the deck and go to the rail. And you do both sides like this. So when you are finished with the deck and the rail, you stop the scan, you flip the board, and then you do a second scan for the bottom. And then we will merge it in the Shape3d software. Okay, so now I have my two scans, the deck and the bottom here. So we did the scan with like 4 mm resolution. It doesn't mean that the precision is 4 mm. It's actually much better than that. It's better than 0.1 millimeter, but it means that it took the meshes of about 4 millimeters. And we use the options targets plus geometry. No texture here. So first thing we need to do is remove the scan of the table, for example. So for that, I select the connected entities, Control select, and then reverse selection, and then delete. Okay, and then I do the same for the bottom here. And now we go to merge scans. So we use surface merging and not target merging because we don't have targets on the rails. And we go to merge scan number 1 and scan number 2. We can lower the resolution to 1 millimeter, keep original scan, and lower the max distance and go to best fit. And you see it works perfectly. So we go to merge. Okay, so Now we have the merge scan here, and we need to convert it to meshes here. You see the surface here has a lot of details because the resolution is 1 millimeter, so it means that the meshes are about 1 millimeter, but we can go to 4 millimeters, and we need to fill in the targets. We can optimize the surface a little and automatically fill the holes. We can do all that and go to apply. Okay, and now we go to create meshes. So we can shut down the scans, only use the meshes, and go for basic repairs. So it will remove the kinks, small holes, things like that. We go to OK. Okay, the scan looks very clean. If there were some big holes remaining, we could fill them out with the fill holes function. And what we can do is remove the thin plugs with the defeature function here. So we select the brush here, press Ctrl, select the thin plug area, and press defeature. Here it's corrected, and now we can do it with all the other plugs. Okay, we could do it with the tape, but it's not very useful. And we could also do it if we see some kinks, for example here. Okay. Another function we can use to smoothen the, the irregularities due to the wax here is a smooth function here. So we select the wallboard and go to smoothen. We can go to 100%, increase the iteration if you want, and then set the max deviation to, let's say, 0.2 millimeter, for example. You see it's smoothen the wax a little, and the bottom is already good. We can go a bit further. You see it's even smoother. Now if we look at the number of meshes here, we see it's very big, like 150,000 meshes. That would make the importation in Shape3d a little slow. So what we can use is the decimate option. So we go to press OK for the smoothen, and we go to here decimate. So here again we can go to 100% and set the max deviation to, we can try with 0.1 millimeter, so we won't lose any precision here. And we go to apply, and we see it already lowered the number of meshes to 12,000. And we can show the meshes here. So you see you have bigger meshes on the flat parts and smaller meshes on the rails. Okay, now last step, if we apply, is align the board with the axis. So we go to basic alignment, align with origin, and you see the board is automatically aligned with the axis. We align and now we can export as an STL file shortboard 2 and we save. Now let's see how to import this STL file into Shape3d using the scan import function. So we go to File, Scan Import, and we browse to select this STL file. So here is our scan. In Shape3d, when you import a scan, the nose of the board needs to be on the right hand side. So here we need to reverse the direction of the x-axis here. Okay, you can see that Shape3d has done some slight rotation here to ensure that the imported scan is as symmetrical as possible. So here you can see what is imported by Shape3d from the scan. So there is it extracts the outline of the board, the stringer curves, and some cross sections here, the slices. You can shunt the number of imported slices. Usually 5 slices is enough in Shape3d to design a board, but here we usually import more and then we can delete the unnecessary slices later on. And if we look at the front here, you have the right side in green, and here we superpose the right and left side to check the symmetry. And as most of the board are usually slightly twisted and sometimes one rail is thicker than the other, it's usually not perfect. So then you can use to import only one side or the other, or you can import both sides and do like an average of the two rails, but it usually gives results that are not as clean. So if we look at the cross section here, we see that Shape3d has placed a green point at the apex of the slices, an orange one on the deck, and a blue one on the tuck of the bottom rail. So the tuck of the bottom rail is automatically detected by Shape3d. It places it where the max change of curvature is. So this works very well when the scan is clean, but it's not always the case. But so it looks good here, and the green side looks good, so that's the right one. And we check automatic fitting and go to import. So Shape3d is now automatically fitting the outline curve, the stringer curve, and the slice curves to the scan data. And it's making a model with the right dimensions. Okay, so here is the result. We see that the outline curves is fit perfectly. The side looks okay. And here we look at the slices. It looks correct. Now let's look at the details. If we look at the profile, we see that the bottom stringer curve is not perfect here because maybe the scan was a little bit rounded. So we can select the tail point here, move it by hand to where we think it will be best, then select the arc and go to automatic fitting to get something closer to what we want. And maybe we can check the slices. Usually it's not as good as the tips where there are less scan data and where it's usually not as clean. So you can see the tail slice here is rounded while the real board has a more square rail. So what we can do is copy this slice and paste it here, and then do the correction by hand like that. And we also copy paste it to the tail in case there are some distortions. Okay, now let's check the nose. We have the same problem, so we copy, paste it, and then do some adjustment. Okay, so now we have something clean. And what we can do now is load the STL file as a ghost board to compare with what we design with even more precision. So it will load the ghost with automatic alignment and rotation. Okay, and here so the outline of the ghost board is in blue, and we actually can't see it because it's exactly the same. Same for the profile. And what is interesting here is to compare the cross section, and we can compare it at any position along the length of the board. So we see that it fits perfectly, except we set the rail a little bit sharper than the result of the scan at the tail. And if we go to the nose, there are slight differences, but you can see that's because one side is actually thinner than the other. So one side is good and not the other one. But overall, it's pretty good. So you have a very good precision here. What we can do also is load a picture of the board as a ghost image to place the fin plugs correctly. Press Shift to rotate and place it correctly, and Control L to lock the image. We can see that the outline of the picture is not exactly the same as the scan. That's because most camera do some distortions. That's why it's much better to use a scanner than just a picture to copy a board, but it's far enough to put the fin plugs. So you go to plugs wizard, set 5 plugs, it's fusion here. We can also put the leash plug. Okay, and now we can move the fin plugs by hand. Maybe the tilt angle is off. Here is leash plug. And now if we go to 3D, we're good. We can even add a stringer to make it more realistic. Sometimes it's really nice to see the board as it's in reality. And here we go. You have your finished board that you can cut with a CNC machine now and reproduce and even modify in the future. Now let me show you another scan I did. So that's a wing foil board. The shape is a little bit more complicated than this short board. The rails have steps. It also has a traction pad that I couldn't remove. And it has like very thick rails, so I could place targets on the rails and use the targets for the bottom and deck merging. And now if we import this scan in Shape3d. Let me show you. Let's load the STL file I exported earlier. We set the correct axis directions. We can set more cross sections here to get cross section from both sides of the traction pad. And we can see that the auto detection doesn't work perfectly here, so we can use this option to place rail point manually as a percentage of the width. It looks correct, so let's import this and do the automatic fitting. Okay, so the automatic fitting of the outlines looks correct. Profile looks correct except for here where the traction pad here, so we'll have to do a correction of the stringer to remove the thickness of the traction pad. So we can start here at the tail, and we can do this correction by hand. So the point here is to check that the thickness on the slices looks okay. Then we can delete that kind of slice where the traction pad is too big. And you need to do a slight correction on the other slice here to fit the data without the traction pad. So maybe let me show you directly the result after cleaning. So I cleaned the slices, and I also added the kind of bat tail here using a 3D layer. And I added the plugs. We can load the STL file as a ghost file to compare again. So we need here to reverse the x-axis. Okay. And we can compare the cross sections from tail to nose. You see here there is a slice asymmetry of the original board that we corrected, and we have the bat tail here. And we can also compare the ghost board with the final design in the 3D, and we see that it's very close except for the traction pad. So here we are. So that was a quick overview of what you can do with a laser scanner and Shape3d. It's a very good tool to duplicate a board that has been unshaped, for example, and it's fast. So basically you scan a board in about 15 minutes, and then the importation in Shape3d will more or less take the same. For more complicated shapes, then you can go to 30 minutes to really do the details of the shape, like channels, swallowtails, or things like that. And then you can keep your design, modify them, CNC cut the files, etc. So I hope that was useful, and see you soon on the Shape3d channel.